This tank costs approximately $10 million per unit. Some configurations are even more expensive than the M1 Abrams or the Leopard 2A7. For a nation that officially renounces offensive warfare, this price tag seems paradoxical. We are talking about the Type 10, a tank designed not for a global war, but for the specific constraints of Japanese territory. Here, broken records don't matter. Infrastructure compatibility does. Inside Japan, most bridges are rated for a maximum load of 44 tons. This automatically rules out heavy tanks weighing 60 tons or more. Therefore, the Type 10 maintains a base weight of 40 to 44 tons so it can traverse the standard road network without the need for bridge reinforcement or pre-planned engineering routes. This directly impacts deployment speed. The vehicle must be transportable across the island via civilian roads and ready for combat within hours, not days. No disassembly, no heavy transporters, and no infrastructure prep required. The result is a stunningly adapted tank where every technical decision is tied to a specific limitation. Weight to bridges, dimensions to narrow roads, and the high price to the necessity of fitting a modern main battle tank into the realities of island defense. To understand how Japan arrived at this logic, we have to go back nearly a century, to the moment its tank forces first began to take shape and drew very different conclusions. July 1937. A full-scale war begins between Japan and China. The main battles unfold around Shanghai and along major railway hubs. It is here that the Japanese army first uses tanks not as a novelty, but as a dedicated breakthrough tool. Their arsenal consists of light and medium machines, primarily the Type 89 I-Go and the Type 95 Ha-Go. By modern standards, they are primitive, armor up to 17 millimeters, speeds of about 40 kilometers per hour, and 57 or 37 millimeter guns. But in 1937, it is enough. The key difference was how they were used. The Japanese didn't tether their tanks to the pace of the infantry. They used them for flanking maneuvers, rear area strikes, and suppressing pockets of resistance. Against a Chinese army with almost no anti-tank weapons, the effect was instantaneous. In the early months of the campaign, Japanese mechanized units covered dozens of miles on roads never intended for heavy equipment. This led to a crucial realization. Mobility and logistics are more important than armor thickness. A tank that can reach the objective quickly is more valuable than a tank that is simply well protected. This experience became hard-coded into the high command. Tanks were seen as tools for rapid pressure, not mobile fortresses. This mindset would define the Japanese approach to armor for decades to come. But there was a hidden cost to this success. Japan bet everything on mobility and underestimated the advancement of anti-tank weaponry. When the conditions of war changed, this early triumph would turn into a severe crisis. Between 1938 and 1941, following those initial successes in China, the Japanese military made a choice that would prove fatal. That choice is linked to Hideki Tojo, one of the most influential military leaders of the time. Tojo placed his bet not on tanks but on infantry, artillery, and aviation. In his view, the coming conflict would be a war of islands, jungles, and limited communications, where heavy armor would be useless. Tanks were relegated to secondary support roles rather than being treated as an independent force. This decision was immediately reflected in the numbers. Armored vehicle production began to shrink as planes and warships took priority. As a result, by 1941, Japan possessed roughly 2,000 tanks, most of which were light machines with armor incapable of withstanding modern anti-tank weapons. While Germany and the USSR were building massive tank armies and mastering deep operations, Japan effectively froze its armored doctrine in time. New projects appeared but never reached mass production or received priority. The tank was no longer seen as a tool of the future. In the early stages of the Pacific War, this seemed justified. Opponents were poorly equipped with armor, and island combat appeared to confirm the dominance of the infantry. But the situation changed rapidly. By 1943, the U.S. Army had saturated its forces with anti-tank guns and medium tanks, against which Japanese armor was powerless. The decisions made in the late 1930s were now working against Japan. This tank hiatus evolved into a technological gap that was impossible to bridge during active hostilities. This very gap led to catastrophic production figures in the final years of World War II, a moment when it became clear just how expensive the abandonment of tanks truly was. By 1944, Japan was no longer choosing which branches of the military to develop. It was choosing what could still be saved. Steel, fuel, and labor were funneled into aviation and the Navy, where the payoff seemed more immediate. Tanks fell to the bottom of the priority list. By the summer of 1944, the situation became irreversible. American B-29s began regular bombing raids on the industrial districts of Honshu and Kyushu. Factories struggled, workshops were evacuated, and production chains were severed. Vehicles that were once mass-produced were now built using whatever scraps remained. Production plummeted. While Japan could count its production in the hundreds at the start of the war, by 1945 it was down to single units and dozens. There were no new projects, and modernization was minimal. Troops received whatever could be cobbled together from available parts. The impact on the battlefield was immediate. Japanese units faced American offensives with almost no armored support. Against M4 Shermans and high-density anti-tank units, Japanese tanks were helpless. They could no longer influence maneuvers, hold back breakthroughs, or even buy time. By the end of the war, Japan emerged without a tank school. It wasn't just a matter of losses. They had no foundation for the future. While other powers walked away with a clear lesson, the tank as the cornerstone of land warfare, Japan realized it had missed the lesson entirely. From this point, a total industrial and doctrinal zero, the country had to start over. But this time, it was under a direct ban on war itself. On May 3, 1947, Japan's new constitution took effect. At its heart was Article 9, a clause that changed everything. The state renounced war as a tool of policy and the maintenance of armed forces to wage it. This wasn't an abstract statement, it was a strict legal constraint. Japan could no longer have an offensive army, develop weapons for territorial conquest, or plan operations beyond its own defense. For a nation that had just lost its industry and military expertise, this looked like the end of the road. But this is where the pivot began. By the late 1940s, a compromise was formed: the Self-Defense Forces. Formally, this was not an army. In practice, it was a military force strictly limited to protecting national territory. Every piece of equipment had to fit this logic. For armored vehicles, this meant a fundamentally new approach. A tank could no longer be a tool for breakthroughs or offensives. It had to be defensive by design, mobile within the country, and compatible with civilian infrastructure. Anything that looked like excessive force was immediately met with political and public scrutiny. This unique situation placed Japan in a difficult position. On one hand, they faced the legacy of failure and decades of lost progress in tank development. On the other, they were bound by a strict legal framework that prohibited copying foreign offensive doctrines. This combination of defeat and prohibition began to shape a specific logic for future Japanese tanks. It was a logic where offensive range didn't matter. What mattered was how quickly you could plug a gap in your own home defense. The next step was forced. Amidst the Cold War, Japan had to rebuild its armor from scratch, under the supervision of allies and the pressure of a new threat from the north. The 1947 Constitution forbade Japan from waging war, but it couldn't forbid geography. Japan remained an island nation on the edge of Asia, and by the early 1950s, that geography became a problem again. To the north sat the Soviet Union. On the mainland, dozens of tank divisions. Within striking distance, Sakhalin, the Kurils, and the Primorsky Krai. Formally, Japan had no army. In reality, it was on the front lines of the Cold War. The situation escalated sharply in 1950 with the outbreak of the Korean War. As American units deployed to the peninsula, Japan was suddenly left without adequate cover. It was at this moment that the US began to insist on Japan creating its own ground defense forces. Thus, the Japan Self-Defense Forces were born, bringing an inevitable question. How do you hold territory if the offensive is banned, but defense is impossible without armor? The answer was unpleasant but obvious. You can't do it without tanks. Initially, this meant utilizing American equipment, machines designed for different distances, different roads, and a different philosophy of war. They provided a presence, but they didn't solve the issue of compatibility with Japanese terrain. This is where the tension arose that would define the rest of their history. Japan couldn't fight like the US, it couldn't copy the USSR, but it couldn't remain without armor either. This contradictory space between legal prohibition and military reality became the starting point for the rebirth of Japanese tank design, not as an ambition, but as a forced adaptation. By the early 1960s, Japan decided to build its first indigenous tank since the war. Not an experiment or a copy, but a mass-produced machine built at home under the strict limitations of the self-defense forces. In 1961, the Type 61 was commissioned. It was a cautious step. Weighing about 35 tons and armed with a 90mm gun, essentially an evolution of the American school, its armor was modest, making no attempt to match the heavy tanks of continental armies. The vehicle was designed to navigate the Japanese road network and be maintained without complex infrastructure. The significance here wasn't in its combat specs, but in the fact of its existence. The Type 61 became the first mass-produced Japanese tank of the post-war era. It restored the country's competencies: hull design, weapon integration, crew training, and domestic maintenance. However, the limitations were immediately apparent. In terms of protection and firepower, the Type 61 looked like a compromise the moment it was adopted. It was suitable for training and local defense, but not for facing the modern tanks of a potential adversary. Both the military and engineers understood this. Nevertheless, the machine served its purpose. Japan was learning to build tanks again, slowly, cautiously, without sudden movements. The Type 61 didn't claim superiority. It was needed to start the process, not to win the race. This experience would form the foundation for the next step. When the opportunity to move beyond caution finally arrived, Japan would attempt to create a tank of an entirely different caliber, heavier, more powerful, and tailored to a specific theater of operations. By the late 1980s, Japan felt more confident. The economy was at its peak, industry was restored, and domestic tank building experience had been accumulated. At this moment, a key decision was made: to create a machine without the compromises of the Type 61. In 1990, the Type 90 was commissioned. This was a different class of machine altogether. Weighing approximately 50 tons and armed with a 120mm smoothbore gun developed with German technical influence, it featured a modern fire control system, a powerful engine, and high levels of protection. For the first time, Japan's Type 90 was held in the same regard as top-tier Western main battle tanks. However, this tank had a very specific geographical attachment. It was designed primarily for Hokkaido, characterized by wide-open spaces, relatively robust infrastructure, and the direct threat of a potential strike from the north. In this theater, a heavy tank was justifiable. The problem became apparent the moment the vehicle was considered for scenarios outside of that specific island. 50 tons pushed the Japanese road network to its absolute limit. The vast majority of bridges and overpasses in the central and southern regions of the country were not rated for such a load. Deploying the Type 90 required meticulous planning, bypass routes, and occasionally combat engineering support to reinforce infrastructure. In practice, the Type 90 found itself tethered to a single island. It was excellent for Hokkaido, but scaled poorly to the rest of the nation. The tank that was supposed to be a universal asset became a specialized tool. This wasn't a crisis yet, but it was a warning sign. Japan was once again hitting a wall built by its own geography. For the first time in the post-war era, it became clear that increasing technical specifications was in direct conflict with national infrastructure. This conflict couldn't be solved through modernization. It required a completely different logic of tank design. This was the moment the requirement emerged for a machine that could maintain modern capabilities without being held hostage by its own weight and dimensions. The flaws of the Type 90 weren't revealed on firing ranges or proving grounds. They appeared on the map. When the military attempted to plan the deployment of heavy armor beyond Hokkaido, the calculations collided with reality. Japan has tens of thousands of bridges. A significant portion was built in the post-war decades for civilian traffic, not heavy armor. According to road network surveys from the late 1990s, approximately 40% of the country's bridges could not support loads exceeding 44 tons. For a 50-ton tank, this meant that a route couldn't just be chosen. It had to be invented. Every march became a complex puzzle involving detours, speed restrictions, or total movement bans. Reinforcing bridges took time and resources that a defensive force simply wouldn't have during a conflict. The contrast was stark. The Type 90 was technically ready for battle, but logistically incapable of getting there quickly. For an island nation, this wasn't just a flaw, it was a deal-breaker. The Japanese command realized they had reached a dead end. They couldn't keep increasing weight without breaking their own country, But they couldn't sacrifice protection just to fit across a bridge. They needed a new solution, not a compromise on tonnage, but a complete reimagining of the tank itself. While these figures weren't discussed publicly, they were the catalyst for the next project, a machine where weight was a variable, not a death sentence. After the bridge load calculations, the command's attention shifted south to the Ryukyu Islands, a chain stretching hundreds of miles. Here, there is no strategic depth. Every coastline is a potential front line. The reality is simple and harsh. The distance from potential flashpoints to the ocean is often less than a few dozen miles. A deployment error doesn't just mean losing a ridge, it means losing an entire island. In these conditions, reaction time is everything. The geography surrounding the Senkaku Islands added even more pressure. Located roughly 200 miles from Okinawa, any escalation there requires the ability to move equipment rapidly via internal routes without a week of engineering prep. This is where the heavy tank becomes a liability. A 50-ton machine might be superior once it's in position, but it's useless if it can't get there in time. The southern islands are unforgiving. Narrow roads, limited crossings, and almost no alternative routes. The command reached a definitive conclusion. For the south, they needed a tank that could be moved immediately across existing infrastructure without reinforcing bridges and without being tied to a single region. Weight could no longer be a constant. It had to be adaptable to the mission. Geography moved from the background to the primary requirement. This necessity launched the next step, a project where mobility and infrastructure compatibility were the starting points, not the limitations. In 2002, the Japanese Ministry of Defense formally launched the program known as MBTX, Main Battle Tank X. This was not a modernization of the Type 90 or another mere upgrade. The document stated clearly from the outset, a fundamentally new machine was being created for the conditions of the entire country, not just one island. The requirements were stringent from the start. Combat weight, no more than 44 tons in the base configuration, allowing the tank to traverse the vast majority of existing bridges. At the same time, the protection level had to meet modern threats, not in theory, in production. Then, it got even more complex. The tank had to retain 120mm armament, a full fire control system, and digital management tools. It needed to be integrated into a universal C4I system. The vehicle shouldn't just fire, it had to see the battlefield and exchange data in real time. Mobility was a separate priority, a speed of approximately 70 kilometers per hour, and the ability to reverse at high speeds to quickly pull out of engagement zones in narrow areas. The suspension had to be adjustable, with the ability to change ground clearance and hull angles. On paper, this looked like a contradiction. Lightweight yet protected. Modern yet infrastructure compatible. Powerful yet not heavy. At this moment it became clear. If these requirements could be combined, Japan would have a tank that simply didn't exist before. If not, the project would end as another compromise, as seen in the past. MBTX didn't just launch a new vehicle development. It signaled a departure from the old heavier is better logic and forced a search for solutions where weight became a manageable parameter. The next step would show how far engineers were willing to go to ensure these requirements didn't just stay on paper. In 2006, the MBTX project moved beyond blueprints. A prototype was rolled out for testing, which was immediately judged not by maximums, but by the harshest criterion, weight and infrastructure compatibility. The base configuration clocked in at roughly 40 tons. This wasn't an arbitrary number. The vehicle was run through routes where the Type 90 had previously been banned, standard bridges, civilian roads, and typical interchanges. The results were recorded dryly. Most routes were accessible without engineering reinforcement. Next came protection. Instead of trying to achieve maximum armor immediately, engineers utilized modular armor. The prototype tested several configurations, increasing weight to 44 tons and beyond without changing the base geometry of the hull. This meant one thing: protection levels could be scaled for a specific mission without breaking logistics. The tests revealed another vital fact. Low mass didn't kill stability during firing. The adjustable suspension compensated for recoil, keeping the platform within acceptable deviation limits. The machine didn't jump or lose accuracy during short bursts. At this point, a phrase previously avoided appeared in the reports: concept validated. For the first time, a tank combined three previously conflicting elements: mobility across civilian infrastructure, a modern level of protection, and full-scale armament. It was no longer an experiment, it was a working blueprint. But the next question was harder. If weight and protection were solved, how do you make the tank see and react faster than the enemy in confined spaces? The answer would become the core of the next development phase. Following the 2006 tests, the key question shifted from which armor is better to when and how much armor is needed. This is where the project finally abandoned the old logic where protection is fixed and always drives weight up. Engineers implemented a modular armor scheme. In its basic form, the vehicle remains around 40 tons, a configuration for rapid movement across the entire country, including regions with strict infrastructure limits. This isn't a training variant, but a fully combat-capable configuration with all weaponry and electronics intact. When necessary, protection is up-armored. Installing additional modules increases the weight to 44 tons, the upper limit for crossing most Japanese bridges without reinforcement. For the most dangerous sectors, a heavy configuration of up to 48 tons is provided, offering maximum frontal protection. Critically, the vehicle's geometry does not change. There is no need to redesign the hull or turret. The time required to switch between configurations is measured in a standard maintenance cycle, not weeks or months. This turns weight from a constant problem into a managed parameter. In practice, this means the same tank can be deployed to the south in a light configuration and then up-armored for a specific threat in a localized area. No vehicle swaps, no theater-specific limitations. This is where the project finally diverged from the Type 90. That tank was either too heavy or useless outside its zone. The new tank ceased to be tethered to a single location. But there was a flip side. If protection became flexible, then firing positions and survival began to depend on the terrain. The next step was, how do you make the tank use cover as effectively as possible without losing accuracy or rate of fire? When weight became manageable, the next problem was obvious. A light tank with flexible armor must survive through positioning, not just raw frontal thickness. This meant the machine had to work with the terrain better than the enemy. The solution was found in hydropneumatic suspension. On the Type 10, this allows the ground clearance and hull tilt to be adjusted directly from the position. The tank can kneel, reducing its silhouette, or tilt forward and sideways to adapt to the contours of the ground. The practical effect is measurable. The hull height can be lowered by dozens of centimeters, and in combat, that is a game changer. The vehicle can peek over cover showing only its turret, drastically reducing its vulnerable profile. In the hilly terrain and tight engagement distances of the southern islands, this provides a decisive edge. The suspension also assists during firing. By tilting the hull forward or backward, the platform stabilizes, reducing the rocking motion after a shot. The tank returns to its aiming position faster, allowing for follow-up shots without wasting time re-leveling the vehicle. This shifts the entire tactical approach. The Type 10 stops being a machine that takes the hit and becomes a machine that ensures it isn't hit at all. Shoot, scoot, and disappear behind the terrain. In narrow corridors of approach, this capability is more valuable than any extra slab of armor. But this approach has a limit. Hiding and maneuvering aren't enough if the enemy sees the battlefield faster and fires first. Naturally, the next stage of development shifted from mechanics to firepower, to how this tank answers the moment contact is made. Once mobility and positional survivability were solved, one question remained that couldn't be maneuvered around. How would the Type 10 knock out a target head-on if it couldn't afford the extra tons of heavy armor? The answer wasn't found in the layout, but in metallurgy. The production of the main gun was entrusted to Japan Steel Works, a company with decades of experience in high-strength steels and artillery barrels. The mission was clear: a 120mm smoothbore gun comparable to Western standards, but optimized for a lighter tank. The key solution was increasing the barrel's operating pressure compared to previous generations of Japanese guns. This allows for the use of high-velocity ammunition without increasing the overall mass of the system. In practice, an APF-SDS, armor-piercing round, leaves the barrel at approximately 1,700 meters per second, which is critical at the short to medium ranges typical of island defense. Crucially, the Japanese ammunition isn't just a direct copy of NATO standards. It is optimized specifically for the ballistics of this barrel and the tank's automated fire control system. This was a conscious choice. Maximum efficiency within its own ecosystem is more important than universal compatibility. As a result, firepower is no longer directly dependent on the vehicle's weight. The Type 10 compensates for lighter protection with muzzle energy and engagement speed. It's not about trying to punch through everything, it's about guaranteeing a kill on the very first contact. This is where it becomes clear that the tank has moved into a different dimension of warfare. It isn't designed for a prolonged slugfest. It is built for the split second where detection and a precise shot decide the outcome. And that leads to the inevitable next question. If the gun is ready, how fast can the tank spot the target and make a decision before the enemy does? After finalizing the cannon, the next question was about what and how much to carry inside. For the Type 10, the answer was unconventional. The ammunition load is deliberately limited to around 30 rounds. This is less than many heavy main battle tanks, but it's a calculated trade-off. Japanese doctrine anticipates short engagements, limited axes of advance, and rapid resupply. The tank doesn't need to operate autonomously deep behind enemy lines for weeks. It operates close to its own depots and bases. The internal layout is built entirely around crew safety. Ammunition is stowed to minimize the risk of a catastrophic detonation if the hull is breached. There are no stray shells in the turret or hull that increase vulnerability. A smaller ammo rack means fewer secondary explosion factors inside the cabin. This directly dictates tactics. The Type 10 isn't meant for a war of attrition. Its job is initial contact, rapid results, and repositioning. Every shot must be calculated, not just part of a long-distance duel. There is also a logistical calculation. A smaller combat load reduces weight and simplifies maintenance. In island defense, where routes are restricted and reaction time is everything, this means a constant real-time data exchange with neighboring tanks, command posts, and reconnaissance assets. A target might not even be spotted by the crew itself. It can be handed off through a secure data link. The practical effect is simple. The crew receives coordinates, target type, and priority levels before they even make visual contact. The gunner doesn't have to hunt for a target. He simply confirms it. The commander doesn't have to sift through the chaos of battle. He makes decisions based on filtered, actionable data. In the confined spaces of an island battlefield, this saves seconds, and seconds win engagements. The system allows for the simultaneous tracking of multiple targets, distributing them across the entire unit. One tank won't waste a shell on a target already assigned to another, and no one duplicates the work. The unit's firepower ceases to be just a collection of individual guns. It becomes a coordinated strike. This is critical for the southern island chains where space is tight and contact is instantaneous. Here, the winner isn't the one with the thickest armor. It's the one who understands the situation first. At this point, the Type 10 moves beyond the definition of a traditional tank. It stops being an autonomous combat unit and becomes a node in a massive network where information is valued as much as armor or caliber. But this comes with a price. A network requires stability, secure channels, and highly trained crews. The question then becomes, how reliably does this system function when the tank is maneuvering at its absolute limit? Once the network provided the time advantage, the focus shifted to execution. Identifying a target is only half the battle. You must be able to change positions instantly. For the Type 10, mobility is a form of protection. Its power plant pushes out about 1,200 horsepower. With a combat weight of 40 to 44 tons, this results in a power-to-weight ratio of roughly 27 horsepower per ton, providing explosive acceleration and agile maneuvering over short distances. On the highway, it hits speeds up to 44 miles per hour. A key detail is the transmission. It allows the tank to reverse at high speeds nearly as fast as it moves forward, without having to turn the hull around. On narrow roads and short defensive lines, this is a lifesaver. Fire, retreat, and reposition without wasting time or exposing the vulnerable side armor. Paired with the adjustable suspension, this changes the rhythm of the fight. The tank doesn't hold the line. It constantly reshapes its position, minimizing the window in which the enemy can return fire. On the islands, where distances are short, this is what keeps the crew alive. Mobility here isn't about a 100-mile march, it's about seconds. It's about the ability to instantly break contact, slide behind the next fold in the terrain, and re-engage targets already highlighted by the network. But high dynamics demand a high level of control. The machine must remain predictable for the crew, and the systems must remain stable during violent maneuvers. This is where mobility, fire, and the network converge into a single, reliable platform. The Type 10 was never meant to be a universal answer to every war. It wasn't benchmarked against foreign machines. It was measured against Japan's own roads, its own distances, and its own reaction times. In its final configuration, The tank stays within the 40 to 44-ton range, scalable to 48 tons, allowing it to traverse the majority of the nation's road network and deploy without engineering prep. It combines a 120mm main gun, high mobility, adjustable suspension, and total network integration, not as separate features, but as a single, cohesive tool. In practice, this means the Type 10 isn't designed for deep breakthroughs or prolonged wars of attrition. Its mission is to quickly plug a gap, deliver a precision strike, and vanish before the enemy can process the data. It is a tank built for a reality where failure isn't measured in miles of retreated territory, but in the permanent loss of a specific piece of land. The $10 million price tag isn't a luxury. It is the cost of adapting modern armor to the rigid constraints of an island nation. Where other armies solve problems with mass and numbers, Japan solves them with compatibility and time. Ultimately, the Type 10 didn't become the heaviest, the most armored, or the most numerous tank in the world. It became the most precise. It is tuned to its own geography, its own infrastructure, and its own defensive doctrine. And that is its defining characteristic. It isn't a tank built to defeat everyone, everywhere. It is a tank built to never be late.